Hello everyone. For module 7, let's talk about I/O. So, if you may remember, the first module of this course, we discussed the different internal blocks of a computer, such as the input, the output, memory, ALU, and control. Now, what's inside the processor, we've already discussed before. We have the single cycle. We had the single cycle processor and the multi cycle processors. So we already know what happens in there. We know about memory because that's what we discussed in the last module with the cached memory, and we know how the CPU and the memory exchange data because we've discussed that in the CPU. Now we have to talk about the last part of the course, which is the inputs and the outputs. How do they work, and how does the processor interact with the inputs and outputs? Now, for I/O, we have some interface hardware that is for say a peripheral device. Let's say this is a peripheral, maybe your keyboard, maybe your monitor, and it has associated data and status registers. So the peripheral device puts its data inside the data register, or rather, we can also say put in data that we want to write into the peripheral device into the data register, which the device then uses. Now, we also have control circuits that control the peripheral device, that is whether or not it's enabled and so on and so forth. Also, its configuration. So, usually processors are much faster than input-output devices. Our input-output devices, they can sometimes work in the range of kilohertz or even just to normal seconds of time domain resolution. So our processors are usually much faster than these I/O devices, so we don't actually have to take them um, like very much into account for every cycle, for example. So what happens is that we tend to give an instruction or a request to a peripheral device, and while waiting for the peripheral device to finish performing that instruction or to finish servicing our request, we give delay spots to the CPU, which allows us to wait for the peripheral device in order to finish, and then we get the valid data from say the data register of the peripheral device. Now, how do we tell whether or not the peripheral device is finished with an instruction or is busy or still busy? Well, that's why we have the status register, so we try to see what's inside the status register. Of course, the status register isn't always necessary, as we will see later. But the main principle how we work with these things is memory mapped I/O. So what does that mean? That means our I/O devices are connected to specific spots in memory, like so. So this is an example put forth by the Harris and Harris book, and these are actual memory mapping addresses for the peripherals of some ARM microcontroller, if I remember that correctly. And so you can see here the system timer, some other external timers are some of these are on chip, some of these are off chip, of course, and these timers are mapped to specific memory addresses whenever say we want to change their configuration, or we want to take some of their outputs, then we read their status and data registers. PCM audio is also here. GPIO. I don't know if you guys have worked with microcontrollers yet, but GPIO is basically where you get a 1 or a 0 on the output of a specific device, and so it's one of the most basic IO parts that you have. The SD card controller, actually our hard disks and our secondary storage are also usually memory mapped I/O. Now, some of all of these we're going to discuss later on in the communication protocols part of our of the I/O of module 7 rather. So Device will only respond if its address is accessed, and this is why we need an address decoder. This is also the reason why, say, we will have enables or write enables on the peripherals, so that the peripheral will know whether or not we're talking to it or not. Also, but some of that is also the job of the communication protocol. The communication protocol can tell a device whether or not you are talking to it, depending on the communication protocol. But this is a concern of the specific implementation of our device. So say for example, if the protocol was USB, this is a microcontroller, so it doesn't have USB anywhere here. But the USB protocol will also have some addressing some addressing protocols, some addressing capabilities here and there. That's why we can use USB hubs. Now, mapping I/O to memory spots is common because it simplifies the software. That is, say, if you had a temperature sensor, you can just simply read the spot in memory in your software and not even care whether or not it's a peripheral. All you need to do is read a spot in the memory but first you have to make sure it's valid, of course. But you all you have to do is read the spot in memory, and you get the data you want. So how does the processor communicate with our I/O devices? Well, let's see. Mu here is our processor. So for polling, this is what happens. So the microcontroller keeps checking the status register. The status register will say whether or not the device is now ready to be read. Um, this is for input devices. And when the status register says it's ready to be read, the microcontroller takes the data from the data register, and that's it. Now for the interrupt style of communication, the peripheral, say this keyboard, for example, whenever a key is pressed, it sends an interrupt, something called interrupt, to the microcontroller, which interrupts um, the processor. That is, the processor is supposed to stop working on whatever instruction, or to skip, rather, go away from the current instruction that it is executing, and start servicing whatever the peripheral needs. In this case, for a keyboard, it has placed a key press into its data register. So then the processor or the microcontroller needs to read that and do something with it. Say, put it into the into input buffer. So say stdio buffer number one, I think, is the input buffer for Linux. So that's what we do to service the inputs for the I/O processor. That's actually interesting because how does the computer know where to place the inputs in memory? Well, each process has its own input buffer, right? And the currently activated process, like the terminal that you're clicking on right now, it's the one that has keyboard capture, is what it's called. And when they have the keyboard captured, that's how the OS knows to place the keyboard data into that process's input buffer. Now, direct memory access is something else. You can see that for this one, the whenever the interrupt happens, the microcontroller needs to see um, needs to see to it that any sort of long communication with the peripheral device is done during the ISR until the entire transfer is over. And what happens there is that when, say, for example, you have an SD card like this, um, right, yeah, there. So whenever, say, you have for example, an SD card like this, it's going to interrupt the processor whenever it wants to send data, and then so um, the processor takes data, right? But the SD card wants to send more than one batch of data. It can only send, say, 4 words at a time. but the SD card is trying to send a total of 2 GB of data. So it is limited by the speed of the SD card, and and the data batch that it can transfer. It cannot transfer all 2 GB at once. It's also limited by, say, the communication protocol. So what happens here is that during the during the interrupt service routine of the microcontroller, it has to also poll the status register still. It has to confirm whether or not the SD card is trying to send some more data, and then service has as well, giving us a very heavy interrupt service routine. Now, direct memory access, we have some sort of external hardware to do that for us. So the microcontroller, whenever it wants to say do something with a peripheral, it just tells it to some hardware, which we call the direct memory access controller. And the direct memory access controller basically gives all the peripheral needs. It controls everything, and it only takes cycles from the processor whenever it's actually absolutely necessary. That is, whenever something is ready to be written. So all the polling of status and whatnot, that is done by the direct memory access controller. So let's see. For an example of the first one, that is polling. Uh, okay, so say for example, this is the program we have for polling. Let's define this section as with the label that is wait k, and let's use a command called test bit, and we check bit number 0 of the status register. Let's say that the thing that we're polling has at bit 0 of status is ready status of keyboard, and bit one of status is the ready status of, say, the monitor. So first we're going to test bit 0 of status to check whether or not the keyboard has been pressed and is ready to send information. So if it's not, that is, if bit 0 is 0, we keep polling. So we still wait for the character to be entered. But if bit 0 is 1, then that means the key has been entered. So that means we transfer the data from the data in register to the register R1, the internal register R1. Now, what do we do with that character after? Well, next we check bit number 1 of the status register to check whether or not the monitor is ready to display the character. Now, since so we branch to 0, we branch to wait D. We poll again if if the monitor wasn't ready. But if the monitor is ready, we put in the character that is in R1 into the data out register of the display, and then we store the contents of R1 into R0, and then we increment the pointer. Now, next we check whether or not it's a carriage return character, that is the enter key, and uh, if it's the enter key, for example, if it's not the enter key, rather, for example, we go back and check for more inputs. But if it is the enter key, then we stop trying to get the inputs, and we we say send um, the entire line to the monitor. Um, uh, yeah. So we send the entire line to the monitor if we are done waiting for everything, and then the process uh, say the process that called this entire input output sequence, we're going to go back to it since it now has the data that it needs, pointed to by R0. Now $0 is the end of file. So we usually put end of file at the end of every file. But that's a part for Linux management. Though it is a UTF-8 character, so it's not just Linux that does that. But yeah, basically, whenever you want to code for something that polls, that's basically how it works. You will learn more about doing this probably in Go A115. So since we've polled like that, we'd want to see how much overhead there is for polling. So let's say, for example, there are these statistics for these are given this data for polling. We want to we want to determine the fraction of time spent, say, polling a mouse for a CPU. If the mouse needs to be polled 30 times per second. So here, and the CPU clock is 500 megahertz, which corresponds to a 2 nanosecond period. We use 400 clock cycles per polling, so 400 times 2 nanoseconds would be 800 nanoseconds spent per poll. Now, since we have 30 polls per second, then the fraction of time we spend polling for the mouse would be around 24 microseconds per second. So that is the fraction would be very, very small. So 24 micro. Um, 24 micro. If you want to convert that to percent, feel free. But this is the fraction in decimal form, just with the decimals offloaded as the micro subscript. So let's say we had a hard disk instead. This is still 2 nanosecond. This because it's still 500 megahertz. Now, if the hard disk transfers data in forward chunks, transferring at 4 megabytes per second, let's see. So how many transfers per second do we have? And so each of those transfers needs to be polled. So each of those transfers for per second is um a poll completing. So by analyzing how many transfers per second that we do, we get the amount of polls that we do per second as well. So let's say 4 megabytes per second times say 4 bytes per word, we get the number of words per second times how many words we transfer every transfer. That is 4 words per transfer. A transfer is a single poll, and from here we get the number of polls per second, which is around say 200 oh fraction of time spent. So we still need to multiply 800 nanoseconds per poll, which gives us 4 over 16. That's uh 25k times 800n, which is around 200 uh, milliseconds per second, which is around one-fifth of the time spent polling for the hard disk at 4 megabytes per second. Now, 4 megabytes per second is actually a pretty slow hard disk. So, we'd want a better way to process this. And one of the better ways is probably by sending interrupts. So in interrupt-based I/O, each device is connected to some sort of switch that sends an interrupt signal to the processor. We can see here this is inverted, but whenever an interrupt is sent by a device, this line is grounded. This line is set to 0, and that means the interrupt signal for the processor is asserted whenever an interrupt is sent by some device. Whenever an interrupt signal is sent by the device, then the whenever an interrupt signal is sent by a device, the processor jumps to the interrupt service routine in order to do whatever response it needs to be, uh, whatever thing it needs to do with respect to the I/O device. So that's basically how the interrupt based I/O processing works. But sometimes we may need to acknowledge the interrupt to inform the device that it can remove the interrupt request. Because if, for example, some devices they assert the interrupt signal and they never deassert it unless they receive the interrupt acknowledge. Uh, and so we need to send it the interrupt acknowledge in order for it to stop, say, for example, interrupting the processor. Because if it doesn't deassert the interrupt, then whenever the processor tries to go back to normal conditions, it will go back to the interrupt service routine if the interrupt signal is still asserted. But what if, for example, we had multiple devices? Well, the interrupts associated with multiple devices um, will all be coming from the same place, so we don't have any way to actually differentiate between the interrupts. Now, there are many ways that we can go about this. Something that one could do in a microcontroller is to merge all of the interrupts that everyone is sending into one big ISR. So then, in the ISR function, for example, we check so we check the status. So the status of we check the status of every peripheral and check whether or not it needs servicing, and then uh, so on and so forth. We do that for every single peripheral until we find the one that uh, actually needs the computer to be interacting with it. But there is another way to go about this, because surely there must be a better way than making that many if statements. If, for example, we have 64 peripherals, or actually even just as many peripherals as your modern day phone has, and it's called vector interrupts. So whenever the device sends a specific, whenever a device sends an interrupt to the PC, it also has to send a vector of numbers. Okay, a vector of numbers, that is a binary number, um, a binary number to the processor, which the processor can then parse to see what memory location it should branch to in order to get to the specific ISR of that peripheral. Now, shown here is an example of how the x86, the Intel processors manage interrupts. It has apparently recently been replaced, but it used to be called the Intel 8259 chip, which is in your motherboard. And what happens is that there are 8 peripherals that can be connected into this IR, that is the interrupt lines over on this chip. And whenever an interrupt is sent on this line, the interrupt comes out here, I think. So the interrupt, a single interrupt, those interrupt lines are combined into a single interrupt line by the Intel 8259 chip. And what happens is that this is associated with each of these interrupt inputs. Now, the say, for example, if the interrupt input number 4 is placed, then the Intel 8259 chip associates a specific number with uh, with that with that spot, and it gives it a number where which the processor um, can then use to uh, can then use using these two slots of this table. It can then compare that with those spots, and then get an address for the interrupt service routine, which it then is able to branch to. And so that's what vectored interrupts are, and that's how seeing as x86 architecture used it. It's a pretty good method of doing it. Now, one could say, okay, we have way more than just 8 peripherals ongoing. So there might be, there might sometimes be more peripherals that we want. And actually, this 8259 chip, uh, this 8259 chip, okay, 8259, okay, I took that from Wikipedia. Um, but the 8259 chip actually has a master and slave version. The master 8259 chips can be connected to multiple smaller 8259 chips, which can then themselves be connected to 8. So that means a total of 8 times 8 peripherals, which means 64 total peripherals. And that's what computers had supported for the longest time. Now, let's talk about the third type of I/O interaction, which is the DMA controller. Since, for example, as I've said before, whenever an interrupt is serviced, sometimes we still have to keep interacting with the device even though we're doing nothing useful. Say, for example, in the case of an SD card or a hard disk. Now, the solution to this is to use some other external digital device that is called the DMA controller. So this is not the processor anymore. The DMA controller is initialized by the processor. So the processor tells the DMA controller, okay, I want you to communicate and facilitate a transfer of information from the SD card to the main memory. I want to load, say, this 200 200 megabyte file from the SD card into main memory. So I want you to do that, and then I'll read the memory after you're done. So then, after the microcontroller is able to tell the DMA controller to start that entire process, that is, the DMA controller requests the data from the SD card. It gives it all the addresses that it wants, and then the SD card gives sets of data depending on the request of the DMA controller, and so on and so forth, which takes a lot of back and forth effort and requires a lot of say waiting for the DMA controller for the SD card to actually be ready to send out the information. The thing about this is, since it's no longer the microcontroller that's doing that, if for example we didn't have the DMA controller, then it's the microcontroller who would have to say request every single address and then wait for a few cycles in order for the SD card to have to be ready to send the output and stuff like that, and then write that to memory. What happens is that if since it's offloaded that work to the DMA controller, the microcontroller is now free to do other things, to execute more parts of the program while the data transfer from the SD card is happening. And what happens here is, but yeah, the CPU is free to do other things while the transfer is ongoing. Now, the CPU will want to use the memory at some point, right? So, well, the CPU usually uses the memory. It's like 20% of all your instructions are memory instructions. So, but the DMA controller also has to write things to the main memory from the SD card whenever the SD card is ready. So, how does that work? Well, uh, I call it hijacking. So the DMA periodically hijacks the system bus, and that is the system bus say is a data line that is shared among um, among all of the things in the computer, and this is connected to, say, the processor, is connected to the memory. And now, we also have, say, for example, the DMA controller, which is connected to the SD card. Now, what happens is that um, the DMA devices, they are given higher priority over the processor in control of the system bus. So, say, for example, the memory tells the DMA to read a bunch of stuff from the SD card and transfer it to the main memory for the microcontroller to work with. What happens is that the DMA, okay, initializes the operation, tells the SD card, goes back and forth with the SD card to tell it what to do and where to find the data, and then starts waiting for the data to come back. The microprocessor, the processor, um, spends its time doing other things. It executes more of your program, and then when the SD card is ready to send the information, the DMA tells the bus, okay, I'm going to take you now. The processor needs to stop whatever it's doing. And so the processor just does that. It stops whatever it's doing, and then the DMA is now free to send the data from the SD card to the memory. So it hijacks the system bus. It takes it from the microcontroller and the microprocessor, and it uses the system bus to send the data from SD card to memory in one cycle. So the microcontroller the microprocessor does not have to execute any other extra instructions apart from the fact that it initialized the process by telling the DMA that it needs this this stuff. And so the DMA device is given higher priority over the processor. But say, for example, you had more DMA devices, more than one, because you can have more than one peripheral, and you had, say, a network controller over here, the thing that receives Wi-Fi, and the let's say, for example, that the Wi-Fi is much more high speed than the SD card that you had. So what happens here is that the DMA controller for the network thing, if it has to transfer um data at much higher speeds, then is given a higher priority. Actually, the network is basically a secondary storage. So let's say, for example, this is your monitor instead, or maybe your GPU. But I think GPUs have a more complicated way of being interacted with. But let's say, for example, that this was like an early day where your microcontroller microprocessor interacts with the monitor directly. So then you would have a DMA that interacts with the monitor, and the monitor wants to be interacted with at, say, 120 120 hertz. So um, then, whichever peripheral needs to be interacted with at the highest speed, it is given higher priority. So, oh, okay. This is the thing that I drew. So you can see here, the main memory. You can choose not to use DMA. Say, for example, for keyboards, interrupt-based processing is actually optimal for printers. When polling is actually also optimal and simple for printers, because all you have to do is check whether or not it's ready for printing and then give it the job. For keyboards, all it needs to do is send an interrupt to the processor and tell it to put it into the input buffer, whatever key was pressed on the keyboard whenever it's done. And it's a bit too much overhead to tell a DMA controller to middleman over a single key press. DMA controllers instead, sorry, this is the processor. DMA controllers instead are used for heavy, large, like bulky jobs with a lot of back and forth, such as interacting with the disk or interacting with a network, as I've said earlier. So, okay. How does the DMA get memory cycles? I did say it hijacks the system bus, but how do we tell it when to hijack the system bus? Well, there are two ways that people tend to go about it. It's called cycle stealing or burst mode. So, the cycle stealing, whenever there's enough to transfer 1 byte of data, the DMA steals the execution from CPU and writes it to memory. So say whenever the DMA device takes 8 bytes from the SD card, maybe every 40 clock cycles, it takes one clock cycle to write that byte to memory, and then it goes back to the control goes back to memory. The control goes back to the CPU, and the CPU is free to do whatever it wants. But sometimes that's a bit too much, because say, for example, if we're just writing 1 byte and the system bus is like 32, or we have like eight buses of 32-bit interfacing with our memory, then that's a lot of wasted cycles if we could just write it all down in one go. So we have another system to do that. That is the block slash burst mode. The DMA only steals the bus once there's enough to write n bytes. And actually, sometimes it can even take more than one cycle to write this. But um, what is ideally the thing is, it also depends on the bus interface of the, say, the secondary storage, or the SD card or the HDD. So say for example, if the HDD gives, say, um 4 megabytes every transaction, then well, I don't think that's realistic, but say for example, the SSD gives 4 megabytes per transaction, then whenever it has sent something, the DMA has an entire 4 megabytes to send. So actually, each of these memory cycle stealing can last for more than one cycle, because the DMA has to transfer a lot of data. But regardless of that, the DMA and the CPU, like the CPU would have taken longer, even if like much longer than the DMA had, because the CPU would have to take just as many cycles to process the inputs from the hard disk. So yeah, that's it for the first part of module 7, which is I/O. And as you in the next if you scroll down, there is the next lecture, which is the final lecture of EEE 105, where we will discuss the communication protocols.